Hi, it's Alex here again, talking to you about measures of variability. And in the previous screencast, we went over some of the basics of variability in terms of calculating and understanding our measure of variation and calculating and understanding our measure of standard deviation. And then some of the ways that we could think about variability using a couple of practice questions. And what we continued to come back to is that when we think about variability, we're often comparing what we see in our sample to this idealized version of a normal distribution. This is the normal curve or normal distribution of a set of scores. And remember, the height here is simply the frequency of particular scores. And we see that in a normal distribution, for example, if we were doing IQ tests are often used as an example for these sorts of things, that 100 is the mean or the average IQ score. And if someone scores way up here at 130, this is a genius. If someone scores way down here at the other end, this is not a genius. All right? And so we say that most people fall within this range here between one standard deviation below and one standard deviation above the mean. That's where most of the people are going to fall. And so we start to think about variation and standard deviation and and variability more widely in terms of this curve, which means that the shape of the curve that we actually see in a distribution becomes increasingly important. And we call the shape of that curve the kurtosis, which is literally the peakedness of distributions of interval ratio variables. And they're all going to be somewhat like this normal curve, but they'll have different characteristics. For example, leptokurtic distributions are tall and thin, so that would be a distribution that looks like this. Okay. Platykurtic distributions are low and flat, so it would be something like this. And mesokurtic distributions are in between, and that's probably more the typical standard or normal curve, the bell curve that we think of. So we can talk about leptokurtic, platykurtic, and mesokurtic as the peakedness of distributions of interval ratio variables. And it's going to be important because if the distribution is tall and thin, if it's in this shaded area, then we see a pretty tight distribution around. Remember, the mean, median, and mode are in the center of those distributions. If they're low and flat, if they're platykurtic, then we see a very broad distribution, and it's going to tell us that there's a lot of variability in that, even if it's normally distributed. Skewness we've already talked about. It can be left skewed, right, because it trails out towards the left. That's also called a negative skew. Or it could be right skewed, where it trails out towards the right, and that's also called positive skewing. And you can actually calculate skewness using a very simple calculation. It's the mean minus the median times 3 divided by the standard deviation. That's it. And that will give you a coefficient that measures skewness. And if we wanted to, for example, we could take the mean, 13.46, minus the median, times 3, divided by the standard deviation for this right here. And if we calculate that out, it will give us an indication of skewness. And we could compare it to the coefficient for skewness for the Stanford data. And if you're interested in calculating this, go ahead and pause the video right now and simply use that formula. It's, remember, the mean minus the median. So mean minus median times 3 divided by the standard deviation. And you could do that for each one of these and see which one is more skewed. And you can see how this calculation makes sense, right? You're literally looking at how the mean is being yanked around by any outliers compared to the median, which is what a skewed distribution is. That's why the tail goes out in one direction. For example, in this right skewed or positively skewed distribution, there's a really high positive score up here. So let's go back to talking a little bit about what a normal distribution is. I mean, in nature in general, there are a lot of things that are distributed with the characteristics that we would call normal. So this normal distribution that we keep talking about really exists in nature a lot, which is one of the reasons why we use it. And remember that there are some unique characteristics of the normal curve. One is that the mode, the median, and the mean all are the same in a normal curve. And it's perfectly symmetrical about the mean, meaning that this side and this side look the same. There also are asymptotic tails, which means that they go out and they get closer and closer and closer to zero, but they never touch zero. It just is infinitely getting closer and closer and closer, but never touching. I can't draw that very well, but you know what I'm saying. And this is generally what it looks like, right? For example, we've already said in nature these things are normally distributed, or a lot of things are normally distributed. So intelligence, height, age, I mean, lots of different things are normally distributed in nature. And this curve actually shows the characteristics we're talking about. The mode, the median, and the mean are all the same. Each side of the distribution is similar, or as we were saying, symmetrical about the mean. And we have asymptotic tails. They get closer and closer and closer to zero, but they never touch zero. Now, one of the unique things, again, about the normal distribution is our ability to use it with standard deviation. So we can actually calculate how far away things are from the mean, or how much standard deviation there is from the mean, using our standard deviation calculations. And it gives us a way of thinking about the number or the percent of cases that are going to fall under the curve in each instance. So for example, the distance between the mean and one standard deviation is 34.13% of all the cases under the curve. Whoops, let me go back this way. So this right here, in here, is 34.13% of all of the cases in a sample or under your curve. And it's pretty standard. If you were to calculate the area that's under this curve, and you were to cut out this piece right here, and you were then to calculate the area, it would come out to be 34.13% of the total. Between 1 and 2 standard deviations is 13.59%. 13.59%. Between 2 and 3 standard deviations is 2.15%. 2.15%. And then between 3 standard deviations and beyond is 0.13. 0.13%. So you can see that we have a lot that are right around the mean. We have significantly less that are between 1 and 2 standard deviations from the mean. Then it's rare to be in this area, right? If you add 2.15 and 0.13, you get 2.28. So only 2.28% of the whole sample, of all the cases, of everything you've got in this normal distribution, is going to be in this part over here on the end. Very rare. And the same is true for the other half of the distribution. So between the mean and -1 standard deviation is 34.13. And you can see that the numbers are the same, just on the other side of the curve. So this 34.13, same for here. 13.59, same for here. 2.15, same for here. 0.13, same for here. So if we look at it, ta-da, this is what we have. And so what we find is that roughly 68% of all of the scores in a normal distribution are going to fall within 1 standard deviation above or below the mean. Now, if we wanted to, we could calculate some statistics where we looked at, this is from a class I taught in statistics several years ago, and I simply took the homework scores for Chapter 1, Chapter 2, and Chapter 3 for all the students in my class. These are the actual scores from that class on the quizzes or on the homeworks. And we could calculate some things with that. For example, we can see that the mode, the median, and the mean, or what they look like for each of those unique homeworks. And we could also calculate the variance and the standard deviation. Let's see what I get after this. Yeah. And I did little histograms. These are ways of looking at, a histogram is another way of looking at a bar chart, another way of talking about frequency distributions, which is what the bell curve is. This is what my distributions look like for the Chapter 1 homework, the Chapter 2 homework, and the Chapter 3 homework. So, for this homework, Chapter 1, we've got mode of 10, median of 9.75, and mean of 9.04. Mean is 9.04. It's been rounded up to 9.0. Standard deviation of 1.43. Look at that, 1.43. And this is what the frequency looks like, and this has had a curve fitted to it. By the way, this is done in SPSS. Very easy to do this kind of a thing and have it fit the curve for you. Now, do you notice anything about this curve? I mean, I know that the bars are sort of distracting, right, because they jump around a little bit, but this curve has been fitted. Anything interesting about this? Is it a normal distribution? Normal? The answer is no. Right? That's not, the mean and the median and the mode are not all the same. It is not symmetrical. Unfortunately, it does not have asymptotic tails. All right, so it's not normal. What is it then? Well, it's skewed. Is it positively or negatively skewed? Well, because the tail trails out towards the left, we call that a left skew or a negative skew. Right? And we could actually take a look at that if we wanted to. How about kurtosis? Is this peaked? Is this flat? Or is it somewhere in between, this curve? Peaked, flat, or somewhere in between? I'm going to go for somewhere in between. Do you remember what that was? It was mesocurtic. We had leptocurtic, platycurtic, and mesocurtic was in between. Okay, if we look at the histogram of the Chapter 2 homework, again, we have a mean of 8.2. We have a standard deviation of 2.58, which, by the way, is much bigger than 1.43. And let's answer the same questions. Is it normal? No, it is not symmetrical. The mean, the median, and the mode are not the same. We know that from the table earlier, where we can see none of these are symmetrical because the mean, the median, and the mode aren't the same. Is it skewed? Yes, again, it's skewed towards the left, so it's a negative skew. What's the kurtosis? Is it leptocurtic, platycurtic, or mesocurtic? Well, it's very flat. It's a very flat distribution. So this is platycurtic. All right, and that tells us something about it. When it's platycurtic, that means that our distribution is much wider. Notice these standard deviations are much bigger. Why is that standard deviation so large, or why is our distribution so flat? Because we have this bad boy over here, which is a little bit of an outlier. Right? We didn't have anybody scoring below 5 on homework Chapter 1, but for Chapter 2 homework, somebody got a 1 out of 10. Either they didn't try, or they really weren't getting it. So we have a very flat distribution, making our standard deviation wider, but we can say that that's partly because of this outlier. And if we were to remove the outlier from the data, we might find a much different distribution. It'd probably be something, I don't know, something more like that. Right, finally, our Chapter 3 homework. Well, let's compare our standard deviations. 2.58 is 2.49 now. We have a little bit more, or a little bit tighter distribution.